Our seniors, are we taking our final with everybody? Are you
Now,
following the schedule?
I have to look at this. I haven't actually looked at the schedule. I think it's like the 26th or something like this. It's normally a week before everybody else takes theirs. But
Okay.
yeah, I'll let you know. I'm gonna take tomorrow. I'm canceling all my classes tomorrow so I can catch up with grading and getting, prepared for this last run, because this last part of the semester is always like a gauntlet, just trying to run the gauntlet. So yeah. So I'll let y'all know all those dates, the dates for our final, all that stuff, whether or not I'm gonna continue the policy of allowing you to exempt the final. I'm not sure about that. I just don't know. That caused some issues last time, so I don't know if I want to do that. But yeah. All right. So let's jump in and come on, PowerPoint. So everything that we're going to be talking about for the next several days is going to be centered around characterizing compounds. And again, if you've taken organic 1 lab, you already have some experience with this. We've done multiple characterization methods. We studied melting points. We studied pH. When we made aspirin, the purple color test with iron chloride, we did NMR and resolved the different peaks in the NMR and figured out which protons they belong to. We also did infrared, so you can see the different functional groups that were present. And so when we talk about characterizations techniques, we just talk about ways to determine the identity of whatever you synthesized. Right? We talked all semester about making stuff. We talked about how to make alkyl halides. We talked about how to use them in substitution and elimination reactions, how to couple them with other alkyl halides. We talked about conjugated dienes and making Diels-Alder products and all of this stuff. And so all of those things, you don't just simply make them and run a reaction, go to lunch, come back, and then start using it, right? Everything you make in a lab has to be verified. And so all of these techniques are verification techniques. These are ways to prove that you made what you claim to have made. And one of the really hallmarks of publishing synthesis especially is what they call a supporting information. And that's a big package of information that's separate from the actual paper that you've written, that has all of the NMR, all the mass spec data, all the infrared data for every single compound that you made. Or if you're doing a total synthesis, every fragment, as well as the total molecule at the end. You have to provide all of that, and it has to go through peer review, and you can't fudge it. I mean, it's either there or it's not. And so the 4 major techniques that are used in organic for characterizing compounds are infrared, and that tells me what functional groups are present. Infrared spectroscopy allows me to see different functional groups and how they basically either absorb or transmit infrared radiation, right? There's a specific group of wavelengths that the infrared region represents, and you basically just bombard a sample with those wavelengths. And when you see absorbances, right, those absorbances correspond to certain functional groups, and every functional group has an absorbance somewhere. Some are very similar, so you can't use infrared by itself. You have to couple it with another method, but for the most part, infrared is a very powerful technique for finding or for verifying that certain functional groups are present. UV spectroscopy is another, and that's just used to identify conjugated pi systems. So you can imagine if you're doing Diels-Alder chemistry and you're making Diels-Alder products, or you're doing some chemistry with aromatics, this is a good method to verify, what products you have. Mass spec is another. We're going to start with that because it's the easiest one to understand. Because if you know how to add up molecular weight and take the sum of atoms that are present, then mass spec is quite understandable. And all mass spec tells you about is size and molecular weight. And so when you think about molecular weight, you don't even need, all you need is a formula. You don't even need to know the structure, right? You don't even need to know the structure. All you need is a formula, and you can know, you can calculate molecular weight. And but mass spec is a little bit more detailed because it gives you the mass of different fragments of a particular molecule. So we'll talk about that. And then we're going to spend the most time on NMR, which is nuclear magnetic resonance. And there are different types of NMR. It basically, proton NMR is what we're going to be studying, and you've already had some experience with that. But there are other types of NMR, different nuclei that you can study. Depending on the type of probe you have in your instrument, you can study proton, carbon, fluorine, deuterium, silicon, boron, oxygen NMR. It just depends on what type of probe you have. But what NMR tells, it's the most powerful of all these methods, and it's the most definitive because it tells us about the carbon-hydrogen framework of a given molecule. All right, so what is connected to what? You can determine connectivity. You can determine the ratios of different protons in a molecule. All of that can be determined from NMR. All right, so these are the four major techniques. We're going to study 3 of them: infrared, mass spec, and NMR. And we'll start with mass spec. Right, so this is an example of an an infrared spectrum, right? And all the spikes that you see going downward, those are absorbances for certain functional groups. And you can see here in this molecule, you have an alcohol, you have an ether, you have an aldehyde, as well as an aromatic. So all of those have key absorbance. That's where they're going to show up in the infrared. All right. Here you have this is a simplified version of a mass spectrum, and every one of these peaks is representative of the mass of a particular fragment. And here we have the molecule itself is pentane. And so pentane basically gets chopped up into little pieces, and every piece has a mass, and those masses show up on the mass spectrum. So we're going to talk more about that later. And then, of course, you've already seen NMR spectrum, and this is a sample NMR spectrum for this molecule right here. So you have aromatic protons showing up down here, and then you have these protons that are like adjacent to sulfur showing up here, and then the protons here showing up here. Right. So again, NMR is your most definitive characterization method. If you do organic chemistry and you don't do NMR, you are wasting your time because you have no idea what you're working with. So the best thing to do is to ensure that you have access to an NMR spectrometer, and you're able to use that in order to characterize your products. All right, this is a sample UV spectrum, and you can see you have certain absorbances that you look for, and you have what's called a lambda max, which is the maximum wavelength that gets absorbed by a specific pi system. And so this is an example of that. All right, so let's jump in and talk about mass spec. And so these instruments that you see are different types of mass spectrometers. All right, so you have your traditional mass spec, which is this big giant instrument up here. And you also have smaller versions of mass spectrum, like mass spectrometers like this one. You have portable mass spectrometers. And I use this example all the time after 9/11, which seems like a long, long time ago. These portable mass specs started showing up in airports, and what they were looking, they would swab your bag and take the swab and analyze it. And what they were looking for was traces of explosives, right? Any type of explosive, because all explosives are organic compounds. The majority of your explosives are some type of organic molecule, right? So you take those explosives, and if they're there, if you run a mass spec, you'll be able to pick up certain fingerprints. They have databases that have all of these fragments stored. So if it's a specific compound, even if it's not that exact compound, if it matches, you're probably going to end up being detained and questioned, at least at the minimum. But these things started showing up in airports. They don't do it as much anymore. But after 9/11, that was a big deal. And every airport had, once they formed TSA, the TSA didn't always exist, but once they formed it, they had these portable mass specs right there by the little X-ray belt where they scan your bags and all that stuff. So they would swab, not every bag, but certain people at random. They swab your bag and test the swab to see if you had any trace explosives or anything like that. And then here at the bottom right corner is a portable mass spec. Now this is a miniaturized mass spectrometer. And it's more than likely very specific to certain types of compounds, but miniaturized mass specs also exist. They even have handheld mass spectrometers. I remember before my wife passed, she was deployed to Iraq, and one of the things that they would have to do, not her in particular, because she was a physician, but one of the things that they would do after they got there and they started running into like a lot of opposition, the Iraqis at one point were using different chemical weapons. So there was a handheld mass spectrometer that some soldiers would use as they scan specific areas. And they would scan those areas with that handheld mass spec to pick up different chemical signatures of different chemical weapons, right? So this idea of miniaturizing mass spec I remember when it was a new idea. Let's put it that way. I'm old enough, I can say that. I'm old enough to remember when they had a conference dealing with miniaturized mass spec. How can we put the machinery, not necessarily the machinery, but just the conceptual part of a mass spectrometer? How can we get it down so small that it fits onto a chip? And now this technology is quite common. All right, so what do we use mass spec for? We use it to identify unknown compounds. That's one of the things that we do. Again, there are databases that exist, and you can run a mass spectrum and then compare it to other spectra in a database to see what it matches up with. Even when we did infrared in lab, when we took the infrared of our aspirin sample, we were able to take the infrared and compare it to other infrared spectra that existed, because these databases do exist. People have curated and collected these data over time. All right. We also use it to quantify known compounds. If you have, again, if you've done a synthesis, you have a compound, a molecule that you made, and you want to publish it, you got to take a high resolution mass spec of it in order to prove that that's the right compound. Right. So all the masses have to add up to the molecular weight of your compound. I already talked about detection of explosives, crime scene investigation. That's another huge area for mass spec. A lot of times, if you watch ID, or if you watch what's the other channel? It's a CNN channel. But anyway, they'll have like a lab. They always have a lab, a crime lab, and they always have some guy or some young lady standing over an instrument injecting something into it. Like most of the time, they're doing either LC mass spec, which is a mass spec coupled with a HPLC instrument, liquid chromatography, or they're doing GC mass spec, where it's gas chromatography. So gas is the carrier And you have a specific type of column in the instrument, and you inject the sample and it passes over the column and you get these chemical fingerprints. And again, you're able to compare it to what's already in a database. And then you can determine contaminants or toxins in various samples. So these are all, not all, but this is not an exhaustive list by any means, but these are some of the methods, some of the applications of mass spec that are used on a regular basis. So what is mass spec? How do we work it? Basically, what do we use it for? How does it work? So you have your sample. You pass your sample through what's called an ion source. Normally, the ion source is an electron beam that bombards your sample with electrons, right? It's just basically a really powerful electron beam that is just basically, if you ever seen Ghostbusters, the old one or the new one, when they had those proton packs and that ray comes out of the proton pack, that's what happens to your sample when it goes into a mass. That's the first thing that happens, is it goes into this ion source and it gets blasted with these with a stream of electrons, right? So you got an electron beam that blasts the sample, and while it's blasting the sample, it is also causing it to fragment and break apart at specific types of fragmentation locations, right? Certain molecules have branches, they have certain sites like allylic sites, they have certain sites like alpha sites next to certain functional groups like carbonyls, alcohols, amines. So those get broken up into little pieces, and those little pieces go into the mass analyzer, right? And when those pieces pass through the mass analyzer, the masses are detected. They pass through, they get detected, and then you get data. So you get a spectrum. And in order for the detector to pick up the fragments, they have to have enough of an abundance. So they have to be present in enough of an amount where they can actually be picked up. Because sometimes your fragments are so small that the masses are so insignificant that they won't get picked up. Doesn't mean that they don't exist, because you can't destroy matter or create matter, but it just simply means that the masses are too small to be detected. Right, so this is the basic layout and the basic operation of a mass spec. Now, the instrument itself is way more complicated. The mass spec that we have at Tuskegee, I think, cost us roughly $500,000, something like that, $500,000 or $600,000. It's a QTOF, which is a time of flight mass spec, and it has a long tube that points up toward the ceiling. And so basically all your fragments get beat up, they get ejected into this tube, and as they fall, you're able to calculate the mass based on the time of flight, right? So let me give you a pictorial of how this works. It's not ideal, but it'll serve the purpose, right? So the first thing that happens again is the electron beam is pulsing this sample, it's killing it, it's beating the crap out of it, right? And so at some point, the electron beam, the electrons encounter an electron somewhere in the orbitals of this CH4, right? And when the electrons smash against one another, they will cause one electron to be ejected from the methyl or the methane group. So you'll see here, right? That's my little depiction of an electron being ejected, right? So you kick out an electron, and then you get this species over here. Can y'all see my cursor on the screen?
Yes.
All right, so you get this species, which is called a radical cation, right? So the radical cation is the original group less one electron. So it's not this group that gets fragmented. It is the radical cation that gets fragmented. And when the radical cation is fragmented, right, what happens is, right, the electron beam is still pulsing. and eventually it's also hitting that radical cation, and it basically explodes it. That's my depiction of that thing exploding into pieces, right? And so down here you get two fragments. You get a radical fragment, you get a cationic fragment, right? Depending on which one is more stable, that's going to determine which one becomes radical, which one becomes cationic, all right? This is how mass spec works. You take a molecule, I don't care how big it is, that molecule, the first thing that has to happen is it has to lose an electron and become a radical cation. I did CH4 because it's the simplest molecule I could think of, right? And that can have a fragment, because I mean, you can't fragment a proton, right? You just can't, it's only one atom, right? But here we get the radical cation, and then we get these two fragments, all right? And so those fragments have masses. The CH3 is going to have a mass of 15. The H is going to have a mass of 1, roughly. So the total is going to be 16. The total mass here is also 16. Carbon is 12, hydrogen is 1, based on their atomic masses in the periodic table. And so that mass is 16, and your fragments have to add up to the original mass. That's very important, a very important point. If you're taking notes, that the fragment masses have to add up to the original mass. Right? You'll never lose atoms or destroy atoms. Right? You only fragment them or repurpose them, but you'll never destroy them. Right? So this is just an overview of what I just said. The electron beam bombards your sample. The sample ejects an electron. The sample becomes a radical cation, and the radical cation gets broken into pieces, and the fragments get analyzed accordingly. All right. So let me pull up a sample, and let's talk about the mass spec, the actual spectrum. All right. So the mass spectrum looks like this, where you have on the x-axis M over Z. All right. Z is the charge, M is the mass, and since the charge is usually +1 of the radical cation, the x-axis also basically represents the mass of the compound. All right. So with that said, the y-axis is the relative abundance, right? So the y-axis is basically the percentage of which fragment is present. All right, so in that mass spectrum, you also have you see that you have multiple peaks in that mass spectrum, right? You have peak at 47, 46, 45, 31, 29, and 15. The other peaks are kind of insignificant. They're just probably, you might have a fragment that also gets fragmented. So you might have a fragment that loses a proton, and you go from 29 to 28, and then you might lose another proton from that fragment to go from 29 to 27, so on and so forth, right? So you have all these peaks, and they have specific meanings, right? So you have your base peak, which is at 31, and that base peak at 31 is the highest abundance, the peak of highest abundance. It also corresponds to the fragment that is the most stable, right? So the most abundant fragment is going to be the one that persists the longest. So that's what your base peak is, and that's why it's at the highest relative abundance. And then you have your parent peak, which in this case is 46. And so with the parent peak being 46, what we're looking at is 45 being the parent, let's say minus a proton, but you also have this peak at 47, which we call the M+1 peak, right? So the M+1 peak is a peak that is the mass plus one. So the M+1 peak corresponds to what we call the isotope peak, right? Every atom has an isotope that has a specific natural abundance where it shows up in nature, right? So carbon has a carbon-13 isotope. It's about, if I'm not mistaken, 1% of all carbon that's on the planet exists as the carbon-13 isotope, right? So every atom has these specific natural abundances where you have the isotope that's represented on the periodic table, which is really an average mass of all the isotopes for that atom. But the average is what we expect to see in nature, and then the isotope, the +1 isotope, is also prevalent, but it's not as abundant. So that's why the M+1 peak is so much smaller than the parent peak. So the M+1 peak is just the mass plus one, and it's representative of isotope peak. So I need to do this kind of old fashioned because I can't find the cutout that I used before. But let me do this because we're gonna have to do this. I want to write this instead of trying to walk through it on the screen, but we're gonna have to walk it down. So I'm gonna import this picture, this screenshot right quick, and switch screens, and then we're gonna walk this example down. All right, any questions up to this point? All right, if you have any questions, feel free to interrupt. All right, let me get this picture resized right quick, and then we're gonna walk through this example. All right, got that. Just blow this up. Perfect. All right, let me share my iPad. We're gonna walk through this example. Come on, Zoom. Don't freeze, don't freeze, don't freeze, whatever you do. Stop sharing. Come on. It's coming up. All right, so again, this is a, let me crop that top off. I don't like that. This is a typical mass spectrum. Of course, it's simulated. I want you to notice we got peaks at, let's see, at 15. All right, we also have peaks at 29. The major peaks, 31, 45, 46, and 47. So what I want to do is go through this, and we're going to actually discuss these, how we can interpret this, and we'll close out with that, and then we'll probably, if we have some time left, we'll apply to an example. If not, we'll apply to the example on Wednesday. So where's my base peak in this molecule, in this mass spectrum? Which one is the base peak?
31.
31. All right. The base peak is readily identifiable. I need a different pen, something lighter. Right. The base peak is readily identifiable. It is the tallest peak in the spectrum. So that's my base peak. All right. My parent in this case is, here at 46. Right, this is my parent peak. So that makes 47 the M plus 1 peak. There is an exception. Sometimes you'll see, hold up 1 second. Sometimes you'll see like what's called an M plus 2 peak. It's nothing special about it. It's the mass plus 2. This only happens when you have a halogen present. Right, so it's only for halogens, right? And let me make sure that you don't think that's a Z. Right, so the M plus 2 peak, that's not on this spectrum because this compound doesn't contain a halogen. But if you have a halogen present, then you can also have an M plus 2 peak. So this is the parent, that's M plus 1, that's my base peak. So those are my three most important peaks that I've identified: the base peak, the parent peak, and the M plus 1 peak. All right. So 45, if you look at that, how much mass would I have to lose to go from 46 to 45? How many grams per mole would I have to lose to go from 46 to 45? So I have a molecule that has a mass of 46 grams per mole. How much of that mass would I have to lose to go from 46 grams per mole to 45 grams per mole?
1 gram.
1 gram per mole. And there's only one atom in the periodic table that has that, and that's a proton. So this is probably, let me fix that. Right, but you can see it's a pretty good size peak. That's 52% relative abundance. So that's an easy fragmentation to knock off a proton, right? Very easy to do that. All right. So let's go back now, and now we're going to interpret this because it's giving us some different compounds that we could choose from. All right. So we got let me try something. All right, so we got that way I don't have to keep switching pens. We got formic acid, which is this compound right here. All right, we have 1-propanol, which is this compound right here. Right, we have ethanol. Of course, everybody knows what that is. It's just CH3 CH2OH. All right. And then we have methanol, which is CH3OH. And isopropanol, which is here. It's just an isomer of 1-propanol. The OH is just in a different spot. So you got all these different compounds. The question becomes, which one of these compounds does this spectrum correspond to? So what we want to do is we can rule out a few of these, quite a few of them. So can somebody look up the molecular weight of formic acid? You have somebody look up the molecular weight of 1-propanol and isopropanol. They should have the same molecular weight. And I have somebody look up the molecular weight for ethanol and methanol. All right, real quick. We got 7 minutes left. Go ahead, Tia.
Um,
We got to speak up a little bit. I can't barely hear you. Go ahead.
it says for formic acid, it's 46.03 grams per mole.
Gram per mole. Good. All right. What about anybody got any of the other ones?
This
I got
is
isopropyl alcohol. Oh, sorry.
Go ahead.
you can
Either one of you gentlemen can go. It doesn't matter.
You can go ahead. I'll go after.
I mean, well, it says for isopropanol, it says 60.1 grams per mole.
60.1 grams per mole. All right, we'll take that out. I agree with that. Go ahead. Who was that? Who's the other person?
That was me, but we had the same one. Was the other one formic acid? Formic.
Yeah, we got formic acid. We got isopropanol. It's okay. One propanol is also going to have the same mass, right? Let me show you why. 60.1 grams per mole. It's the same molecular formula, right? It's you have let me see. You have 1, 2, 3 carbons. And you have here 1, 2, 3 carbons, right? It's the same formula. It's C3. It's just a constitutional isomer. C3, and that's 3, 5, 7, 8, H8. Oh, right. Same thing here. This is C3, H8. Oh, right. So both of those have the same formula. So we're good on those. If you know one of them, you know the other one because they're constitutional isomers. All right. Give me ethanol.
46.07 grams per mole.
Grams per mole. Good. All right. And then methanol. Somebody give me that one.
You know,
Say again. Anybody got that one? Let me see. 15 and 17
0.04.
grams per mole. All right. So now we got our molecular weights, which is a big part of this process. If we look at the spectrum, all right, let's go through and eliminate what we know this spectrum can't correspond to. All right. And the way we do that is let's take isopropanol and 1-propanol. The molecular weights for those two compounds, the molecular weight is 60.1. All right. If that's the case, and if the parent peak corresponds to the molecular weight, right, which it does, let me put that in here. I'm not sure if I made that clear. But this is always the molecular weight of your compound, right? Always. If the parent corresponds to the molecular weight, what would the parent peak be for isopropanol or 1-propanol? What should it be?
46.
Think about what we just said. The parent peak in this spectrum is at 46 because that's the molecular weight of the compound. If isopropanol has a molecular weight of 60, what would the parent peak be?
60.
60, exactly. It should be 60. But do you see a peak at 60 on the spectrum anywhere?
No.
It doesn't exist. And so what that's telling us is that 1-propanol and isopropanol cannot be represented by this spectrum. Neither one of them, because if they were, the parent would be at 60, not 46. Are y'all following that? Is that clear?
Yes.
All right. So the parent peak, if the parent is not present, then the compound can't be represented by this spectrum. Because the parent is the most important thing, because that is what you fragment. That's what you turn into the radical cation and fragment. So 60 is not present. The spectrum stops at 47. So there's nothing past that. So those two compounds can't be there. Does that make sense?
Yes.
All right. What else can we rule out?
Methanol.
Methanol. We can rule that out. what would the parent be for that?
32.
32. And if you look at the spectrum, there's nothing, not only is there nothing at 32, you can't have some higher molecular weight compound in there that's not methanol, right? You see peaks at 45, 46, and 47. If the parent is 32, there's no other mass past that. Everything is going to be that, and then maybe the 33 M+1, and then everything else is going to be less than that. So you won't have that for you don't have that for this spectrum. So this spectrum is not methanol. So it's got to be formic acid or ethanol. It's got to be one of these two. So let's take formic acid down here. So this is again formic acid, and this is, I'm gonna write this out. I feel like I'm doing a Khan Academy video of this black background. All right. So this is ethanol. This is formic acid. Now, what we need to do now is think about the fragmentation patterns. So we have fragments up here at 45, which is the loss of a proton. Either one of those can do that. We got a fragment at 31, a fragment at 29, and a fragment at 15. So let's break up. Let's take formic acid, make it into a radical cation. All right, and let's break it up into pieces. So we're gonna, and we're not doing this at the same time. This is one fragmentation, and then it could also fragment a different way. So we're gonna break this up because this is a carbonyl, and we're gonna break it at the sites adjacent to where the carbonyl carbon is. So we're gonna break it here. That's one fragmentation pattern, and we're gonna break it here. So we're gonna say frag 1, and then this will be frag 2. Hopefully this is making sense. So let's look at what we get from frag 1. So from frag 1, we broke off the OH group. Is that right?
Yeah.
So we'll get OH. We don't know, we'll figure out whether it's radical or cation afterwards. So we'll get OH, and then we'll get this. So let's make this the cation, and let's make that the radical. Because when you fragment it, one piece has to become one or the other. One piece becomes the radical, one piece becomes a cation. All right, and then for frag 2, let's look at that. So we got H, no problem. We're gonna make that the cation. Actually, let's make it, yeah, we can make it the cation. We can, with a proton, it can be either or. It can be a radical or a cation because it's stable as both, so it won't matter. So that plus this. We'll make that, actually, let's make this the cation, and let's make this the radical. That's a little bit more stable. The carbonyl is more stable as a cation because you can do resonance and stabilize it with those electrons on oxygen. All right. Now, what is the mass of OH? H is 16. I'm sorry, O is 16, H is 1. So this has a 17 grams per mole. This is what has to be left, 29 grams per mole, because they have to add up to 46. And then on frag 2, which I didn't indicate here, this is 1. And then over here, this has to be what? 45 grams per mole. Everybody following?
Yes.
Yes.
Yes, sir.
All right. Now, what's missing? Look at the spectrum. What's missing? I got fragments of 17, 29, 45, and 1. What's missing?
31.
31, which is the most important fragment of all of them. And there's no way for me to get to that from formic acid. I can't chop that any kind of way to get a fragment that's 31 grams per mole. What else is missing?
The M+1.
Well, M+1 is a given. You're always gonna see that. So the 47 is always gonna be there because that's not a fragment. That's just a a different isotope. So the carbon in the carbonyl will be carbon 13 instead of carbon 2. So that's always going to be there. What about 15? I can't, there's no way I can get that either. Is there?
Mm.
There's no way I can chop this up to get a fragment of that's going to have 15 grams, that's going to have a mass of 15 grams per mole. So this with formic acid, I'm missing the two really important peaks. And there's no way to get them. So I'm missing 31 grams per mole and 15 grams per mole. And there's no way for me to fragment that molecule to get those fragments at all. So what can we say about the spectrum? Does it correspond to formic acid? Or can we rule that out now?
Yeah.
We can rule it out. Because I can't get the base peak, which is the most important peak in the spectrum besides the parent. And I'm also unable to get that peak at 15. And so I can rule out formic acid. So let's say that here. And actually we're gonna stop. I don't want to go too much further over time. Right? So formic acid is not the compound. So it's got to be ethanol, but I'm not going to go through the fragmentation for that because we already over. We'll finish it on Wednesday, and then we'll start infrared. We'll finish this mass spec on Wednesday. But again, this is the easiest out of all of the techniques. This is the easiest one to understand because it's just adding up masses. If you got a periodic table and you can find the atomic mass of an element, then you can figure out the mass of any fragment. All right. And I know you can do it because, I mean, it's not like y'all didn't just get in college just because. Y'all are all capable of doing whatever you want to do. So this is the, out of all of the techniques, this is the easiest one to understand because just chopping the molecule up, and there are specific fragmentation patterns for certain types of molecules. So we're going to learn those too. And then we'll come back Wednesday. We're going to learn the fragmentation patterns. We're going to fragment ethanol first so we can match it up with the spectrum. And then after that, we'll do a case study, like a crime scene investigation type thing. And then we'll move on to infrared. All right. Any questions? Anybody got any questions about anything? All right. Thank you for participating today. I heard a few more people chiming in, and that's good. Always good to have participation and back and forth, call and response. That's a good thing. All right. I'll see you all on Wednesday, God willing, and have a great rest of your day.
Thank you.